So there can be as many as 10 million viruses in just 1 teaspoon of seawater. So that's 10 million viruses in just something as small as this spoon. But, as they say in The Hitchhiker's Guide to the Galaxy, I recommend that we don't panic. Because most of these viruses, they're not interested in you or any of us humans, but they're very interested in bacteria in that seawater. So I'm really fortunate to be a marine scientist for a job. And what really gets me excited and enthusiastic every day in my research are the viruses in the world's oceans. So this is quite a new area of research in science because our understanding of the sea has really changed immensely beyond just their direct use as shipping channels or for resources such as fisheries. Now, it's true that most research that's conducted into viruses on this planet really focuses on the viruses that cause disease in us humans. So, of course, we're all familiar with headlines around Ebola virus and more recently the Zika virus. But I think that this emphasis on the viruses that cause human disease is really quite a negative one, and it gives us quite a skewed view of viruses in general. And I believe it's time that we redress the balance. So, really, we need to break the barriers that exist in our minds at present, that all the viruses that we share this planet with are bad. And instead, I think we need to open our minds to the many benefits and possibilities that viruses could bring. What if, maybe floating in that teaspoon of seawater, there are viruses that could hold the key to the next great scientific discovery? So what exactly is a virus? Well, very simply put, a virus is quite basic. It's normally just a string of DNA, sometimes RNA, but they have a really big attitude. So standard virus behavior is to invade a cell, hijack that cell's machinery, and then use that machinery to make lots of new copies of itself before finally bursting that cell open and releasing those new viruses out of the cell. I like to think of when a virus takes on something as big as a cell, it's kind of similar to when Luke Skywalker, in the very first Star Wars film, took on the Death Star in just his small X-Wing fighter jet. And what was the outcome of Luke's mission? I'm sure you all know that Luke, the wannabe Jedi Knight, well, he won by completely blowing up the Death Star. So I like to think that when a virus, which is so tiny, like Luke was in comparison to the Death Star, that virus still proves itself to be tiny but a very effective invader. So there's a team in the US at Purdue University led by Professor Michael Rosman, and they've put together this really nice animation that I'm going to show you of what happens when a virus targets a bacterial cell. So viruses that infect bacteria are given a special name. They're called bacteriophage, or phage for short. And I really like this particular phage because to me it looks like the first lunar lander that put us first humans on the moon. It's kind of cute. So what happens is when this virus encounters a bacterial cell, it basically attaches to the surface, the outside of that cell, via specific receptors. And once that phage is attached to the outside of the cell, it can then drill down and puncture a hole into the surface of that cell. And through that hole, the phage can then inject its DNA to the inside of the cell. And once inside, the whole process of making new copies of itself can begin. So what I'd like to do now is to really dive a little deeper into that seawater, that single teaspoon of seawater. So this is the view from the Hubble Space Telescope. And it sends us images of star clusters and galaxies from far off in distant deep space. And this is the view from my microscope of just what exists in that single teaspoon of seawater. So the very nice, big, bright stars that you see in my microscope are in fact plankton, such as tiny one-cell plants called phytoplankton. And the next slightly smaller bright objects are bacteria. But then all the tiny pinpricks of light that you see that fill most of the image in my microscope are in fact viruses. So you can see that viruses vastly outnumber bacteria and other life forms in that seawater. It really is like a viral soup. In fact, someone has gone to the effort of finding out that if you were to lay all the viruses in the world's ocean end to end, they would span further than the nearest 60 galaxies. So viruses are really key, and they actually exist physically on a nanoscale, but their influence is on a global scale. And the key here is the life forms that they infect. So most of the living matter in our oceans is actually microscopic. We cannot see it without instruments such as my microscope. And without viruses, the planetary engines would grind to a halt. And this is why. The key is, who do viruses infect? So the most abundant in terms of weight of that microscopic life in the oceans is in fact bacteria. And again, they've gone to the effort of finding out if you weighed all the bacteria in the world's oceans, how much would it be the equivalent of? And they worked out that all that bacteria would weigh the same as 50 million blue whales. Yeah, oh my God, is right. Again, and I don't think any blue whales are actually harmed in the making of this slide, by the way, like not physically put on any scales or anything. But yeah, so it's really key. And every day, 25% of that microscopic life is killed, is infected by viruses in the oceans. Now that sounds a bit grim, but what that actually means is that the viruses are recycling all the energy and the nutrients that are bound up in those microscopic cells. And they're bursting those cells open and releasing the energy and nutrients into the surrounding seawater for other life to use. So it's really important that viruses are doing this recycling exercise. Viruses are excellent at recycling. Maybe we should all take a leaf out of their book. So I want to pause for a moment and ask you all to take a couple of deep breaths with me. So we take a deep breath in and out. Nice big breath in and out. One of those two breaths you have just taken came from the ocean. Every other breath of air that we breathe was originated in the ocean. And the reason why is because half of the oxygen on this planet came from the microscopic life that lives in the oceans. Half the oxygen is coming from that microscopic life. So they're hugely important. And it's all through the process of photosynthesis. So of course that's the important process we all learn about at school, where solar energy is harnessed and carbon dioxide is removed from the air to make food, and in return oxygen is released back into the atmosphere. Now viruses actually help increase photosynthesis because by recycling the energy and nutrients, they're helping that process click on in a nice way. So that's what I meant by the planetary engines will grind to a halt without that process, because viruses really help those engines keep ticking over. So in fact, viruses, by helping photosynthesis, they actually increase it to a point that they actually help also reduce the amount of carbon dioxide in the air by as much as 3 gigatons of carbon a year. So if we were to remove viruses from the oceans, we would stop that energy and nutrient recycling that happens, and then we would stop photosynthesis, and essentially life would be no more. So even though we do know that viruses can infect everything from bacteria to whales, we actually know very little about them. Viruses truly are the dark matter of our oceans. What we do know is that viruses can help shape populations, they can drive evolution, they can affect the chemistry of seawater, and sometimes they can even influence the weather. We also know that the viruses in the oceans actually represent a huge untapped genetic reservoir, and they contain genes that we have yet to discover. Considering we know nowadays so much more about our human genome, when we actually do the equivalent and go into the oceans to hunt for virus genes, 70 to 95% of the genes that we uncover each time we go out there have never been seen before, and we have absolutely no clue as to what those genes are doing. So it's been 100 years since the first bacteriophage was discovered, and yet we still know so little. Viruses have existed on this planet for much longer than most other biological life, and some people, myself included, I am a true convert, believe that viruses were the precursor to life on this planet. Indeed, viruses have shaped evolution. 10% of your human genome is viral in origin, so we would not be what we are as a species without viruses. And I think that viruses represent a window to our evolutionary past, to where we are in the present day, and they could possibly be a window to our future as well. And we are really on the tip of the iceberg in terms of marine virus discovery. Marine viruses, to me, they represent a source of new ideas and new biotechnology. What we really need to do is start researching more the biological agents that we share this planet with. One of my big concerns is that in the face of growing stresses and pressures in this planet, such as climate change, what are we going to lose in terms of the biodiversity of entities such as viruses before we've even had the chance to get out there and understand and examine them? So one of the really important but unanswered questions is, do viruses play a role in phenomena such as coral bleaching? So of course this year we've had a really sorry episode of coral bleaching. It's been really severe on our own Great Barrier Reef right here on our doorstep. So my question is, do viruses play a role where we see these beautiful, pristine coral reefs, such as this one, teeming with fish life, really beautiful sight to see, turn to this sad and sorry state where a lot of the corals have bleached and may eventually die? So do viruses possibly play a role in this coral bleaching phenomenon? And this is one of the questions I've been focused on in my recent research. Also, we know that corals can be affected by as many as 20 different coral diseases globally, and also, again, locally on our reefs here. And although we do know these coral diseases are going on, we've yet to actually identify a single virus that may play a role in those coral diseases. But we do know that some of these coral diseases are caused by bacteria. So how about if we turn this whole thing on its head and look at it from another angle? How about if we could use viruses to help control that bad bacteria that causes coral disease? We're going to see, with the rise of antibiotic resistance, an increasing use of viruses in what's termed phage therapy to fight bad bacteria. Most of you may not be aware, but we already use viruses in things like our food to fight bad bacteria. So for example, cheese is often sprayed with a cocktail of viruses to fight bad bacteria such as listeria before that cheese is then packaged and sold. So could we use that approach to fight negative scenarios such as coral disease in our global oceans and right here on our Great Barrier Reef? So we also know that viruses can control big algal blooms that are sometimes so huge they can be seen by satellite in space, such as this one off the coast of the UK, where I happen to be from. And viruses can also potentially help control toxic, harmful algal blooms that often result in huge fish mortalities and can threaten human health. I believe as researchers, we really need to get a critical mass, both in terms of personnel and funding, to really research this aspect of marine science in depth. And I believe as a species, we need to adopt a more positive virus-centric view of this planet. So although marine virology is a pretty recent emerging area of research, we actually still know more about deep space, thanks to instruments like the Hubble telescope, than we do about our very own planet and the little biological entities that are floating right here on Earth under our very own snorkel masks. So today, I would like to invite you all on a flight mission of discovery to boldly go where no human has gone before and to embark on a mission to discover just what viruses are doing in our world's oceans. I hope it will be one small step for the humble researcher, but one giant leap for science. I thank you.